All right, it's chip of the day. Today we have an FS8205A. It's an odd part. It's a dual N channel part, but it's not what you would think of a normal dual N channel MOSFET. It's wired funny. Now these chips really are everywhere, but they're only used for one particular thing. If anybody knows something else you can do with these things that might be fun, let me know. But they are used in these little battery charging circuits as protection, okay? And I did another video that showed this diagram, and there's a charge circuit, and then there's a battery protection chip, which is a DW01A, but it needs this external FET to work. And it's this weird dual FET, and so that's what this part is. And what makes it strange is the way it's wired. You can see that it's not two separate devices, it's two devices wired together. So the drains are common. It has the sources and the gates, but the drain is common, which is strange. And then you can think of these protection diodes on the substrate of the MOSFETs block everything, right? You could go positive here, but then you need to go, yeah. So it sort of acts as a good switch. If you turn this guy on, then you need to turn both of them on to get current to flow in this thing. So that's it's kind of like a wired AND. But anyway, let's take a look at some of the specs because it's pretty amazing for such a little part. 6 amps continuous current. Now I always get hung up on these things. 6 amps continuous current, but the package is teeny tiny. Can it really do that? Well, it's got really low ohm resistance, so I guess we can do a quick calculation later. But it can handle 25 amps pulsed. That's pretty amazing. Yeah, so here's its shining data. 21 milliohms at 4 amps. 21 milliohms. So what's a milliohm? Well, it's 0.021 ohms. Okay. 0.021. All right. So if we want to calculate power, it's I squared R. Okay. So let's do a calculation at 4 amps. We have 4 amps squared times R, 0.02. Okay. So let's get a calculator. People say, you should be able to do that in your head. Well, if you're on camera and you're doing a billion things, your brain is overloaded and your brain can't do simple math. It just can't. You try doing YouTube videos on the fly, watching the camera, watching the exposure, watching your audio, trying to think of what you're going to say next, and then do math in your head. Yeah, give that one a try. Anyway, 16 times 0.02 is 0.32 watts. Okay. What did it say was its maximum? 6 amps? Continuous? That would be 36 times 0.02. That would be 0.72 watts. That would be at 6 amps. So, can you see anything I'm writing there? You didn't see anything I was writing there. Anyway, P equals I squared R. 16 times 0.02 is 0.32 watts. So, if indeed that little chip can dissipate 1 watt, which the data sheet says so, I'm just not sure. I really don't know. A lot of times they'll hide the fact that you need extra copper somewhere, but I can imagine maybe a little chip like that can dissipate a watt. I mean, it's conceivable. It could happen. Anyway, that's what this chip is. Let's see here. So let's measure one. All right. I took an old board and I took the chip off of it and I put it on a little breakout board here. So there's a chip on the little breakout board and I've hooked it up, and so we can do the little test on it here. So let's test it. One of them. There we go. It says it's a field effect tube transistor, an NEMOS. VT, the voltage threshold when it turns on, is 0.9 volts, 0 picofarads, 0.2 ohms. So yeah, 0.2 ohms. This thing probably can't measure milliohms, so it's probably as good as it gets. 4 voltage, 0 volts. Yeah, this thing, when it turns on, man, it is on. It is hard on. So we got this funny little chip, and it is, so there's something suspicious about this, so I want to show it to you. So if you take a look at the package, we have 2 pins just for the source. So these are together and these are together. And that may be, so you can put a big fat trace coming through here, right? S1. So you can have a lot of copper going into this thing. So I don't see anywhere in here exactly a layout for the PC board with like that, but it probably does require you to have some copper on this thing in order to get that 1 watt out. But that's just a guess. Data sheets are funny. A lot of times you have to dig through them and dig through them and dig through them and do a bunch of calculations yourself to figure out, oh yeah, I'm probably going to need to do something like that. Really good data sheets will tell you right away, oh yeah, this is the way you should do it. Here's the layout. But anyway, there you go. That was just kind of the funny thing. So when you look at these little guys on these boards, there's a big blob of solder. There's usually a bridge, and there's a big blob on this side and a big blob on this side. So they did pay a little attention to opening that up for the solder masks, which allows these two to bridge together. So there is a little blob of solder on both sides of this part, which I think will give you a little bit more heat sink. Anyway, just a guess. All right, another cautious thing about reading data sheets is it says here drain current in amps, and it says the turn-on voltage. So if you have 1.5 volts on this thing, it turns on all the way it possibly can, and it goes up here to 20 amps. And you go, wow, 20 amps. But it can't do that in DC mode. It can only do that in pulsed mode, and it really should say on this data sheet, should say pulsed current. Shouldn't say just current. It should say pulsed current, and it should give you exactly what does pulse mean. How long is the pulse, and what is the period between pulses? Those are both very, very important things. And I don't think it says anywhere in this data sheet. So a lot of times, if you're a real designer, all right, you will have this data sheet, which you get out of the internet or whatever, and then you decide to use this part. And because you're going to buy a million of them, you have access to go ahead and talk to this company, call them up, ask them, okay, I want the real data sheet, right? I want the safety data sheet. I want the characterization data sheet. I want the reliability data sheet. I want the R&D data sheet. I want all the data sheets you got. Give me all the data. And then if they don't have the data that you see printed, then ask them, here's my situation. Call up their applications engineer. I have this pulse. I have this duty cycle. I have blah, 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 blah. Is that going to be okay? And then hopefully you'll get the answer. But anyway, there you go. Chip of the day was an FS8205A.